Okay, picture this. You are the engineer on the hook for 60 megawatts of raw, unyielding solar power. That energy is flowing rapidly from thousands of sun-soaked panels, and it is entirely your job to make sure it reaches the grid safely, efficiently, and, without any catastrophic explosions. So how exactly do you control that kind of force? Well, today we're taking an anatomical tour of the exact equipment that makes it all possible. We're diving straight into Chapter 4 of the EcoEgypt Utility Scale PV Training Program to really unpack the complexities of medium voltage switchgear. Let's get into it. The heavy-duty cabinet setups you'd find at a massive 60-megawatt plant are incredible. You can really think of the medium voltage switchgear as the ultimate traffic cop of the solar plant. And our source material today draws heavily on the extensive field experience of MSc engineer Amer Awani. He's overseen more than 150 megawatts of PV projects and a staggering 7 gigawatts of MV power systems. Grounding our theory in his actual boots-on-the-ground experience is a great reminder that we aren't just talking about textbook engineering here. This is the literal, critical infrastructure that keeps our lights on. So, to give you a complete picture, our roadmap for this explainer covers 6 main stops. 1. The plant's backbone. 2. Design fundamentals. 3. The 4 cubicle types. 4. Plant protection relays. 5. Switchgear versus RMU. And finally, 6. Real-world field experience. Section 1. The plant's backbone, power, protection, and control. To truly grasp the massive scale of a utility PV project, we absolutely have to understand the core mission of its medium voltage infrastructure. The MV switchgear is effectively the central nervous system of the whole PV plant. It is definitely not just some passive metal box humming in the desert. It's a dynamic, living system carrying out 3 absolutely critical missions simultaneously. First off, it transmits energy from the inverters all the way to the step-up transformers and the utility grid. Second, it acts as this massive shield, detecting and isolating electrical faults, like short circuits, before they can completely destroy your expensive transformers and inverters. And third, it provides control and monitoring by constantly communicating with the plant's SCADA system for remote operation. Moving on to Section 2, Design Fundamentals, building the nervous system. Before a single piece of metal is even cut or a wire is run, engineers have to sit down and calculate some highly interdependent critical design parameters, starting with the rated voltage. This typically operates anywhere between 11 and 33 kilovolts, and that dictates the insulation levels and equipment clearances. Then we've got the circuit breaker current rating, which obviously must safely carry the massive AC currents generated by the inverter output. But here is where it gets really intense, the short circuit level. The switchgear's short circuit withstand rating has to safely handle massive calculated fault levels. We are talking about surviving 25 kiloamps of pure destructive force for a full second. That is no joke. Finally, you have to ensure proper protection coordination so only the faulted section trips, alongside totally seamless grid integration for things like anti-islanding and safe reclosing. Section 3. The 4 cubicle types, anatomy of the switchgear. When we break down the anatomy, this system is actually highly modular. There are 4 primary types of cubicles, or organs if we stick to our nervous system metaphor. First, you have the incoming cubicle, which serves as the main grid feeder. Second are the outgoing cubicles. These are your PV feeders bringing power from the inverter transformers straight to the MV bus. Third up is the bus coupler, which is a vital link connecting bus A to bus B. And fourth is the service transformer cubicle. This one steps power down to feed the auxiliary low-voltage loads. Think things like cooling fans and the SCADA servers themselves.
All right, Section 4, Relays and Plant Protection, the plant's reflexes.
Just like a human body has involuntary reflexes to, say, pull your hand back from a hot stove, the switchgear has protection relays that serve as its digital brains. This is where those dense ANSI protection codes get translated into real-world defense mechanisms. And there is a pretty stark contrast depending on the cubicle. The incoming main grid feeder is your absolute first line of defense, so it requires a heavy, comprehensive 9-relay protection setup. We're talking overcurrent, earth fault, directional overcurrent, and voltage protections like ANSI 27 and 59. Meanwhile, the outgoing PV feeders generally rely on a standard 7-relay setup, which primarily focuses on overcurrent and earth fault isolation. Now, you might be wondering about the ANSI 25 code. The really crucial point here is that ANSI 25 is the sync check function, and it is entirely unique to the bus coupler.
Before the bus coupler's circuit breaker is even allowed to close and connect two separate buses, ANSI 25 acts as the ultimate gatekeeper. It verifies that the voltage, frequency, and phase angle of both sides match up perfectly. Because without it, oh man, you'd risk a catastrophic, completely out-of-sync collision between two massive power sources.
And hey, speaking of catastrophic risks, we literally cannot talk about relays without mentioning the current transformers, or CTs, that feed them all their data. As the training materials specifically highlight, there is a massive hidden danger here. If a technician accidentally removes a shorting link and leaves the secondary circuit of a current transformer open while primary current is flowing, it generates several kilovolts of voltage across those open terminals almost instantly. That is more than enough to cause a deadly electrical flashover, completely destroy equipment, and obviously cause very serious injury. It is a very sobering reminder of the raw, dangerous power sitting inside these cabinets. Section 5. Switchgear versus the RMU. Centralized versus local. It's absolutely vital to understand the difference between centralized and local setups when looking at the overall plant layout. A standard MV switchgear is a centralized, metal-clad modular lineup. It relies heavily on robust vacuum circuit breakers, or VCBs, to handle multiple high-current feeders right at the main substation. The RMU, or Ringman unit, on the other hand, serves a totally different purpose. It's a compact, fully sealed enclosure that is insulated with SF6 gas. You'll generally find these RMUs sitting locally out in the PV blocks, right at the transformer terminals. They provide local load isolation and loop continuity all the way out there in the dusty, high-temperature field. And finally, Section 6, Real-World Field Experience. Engineering on paper is great, right? But operating a live, multi-million-dollar plant is a whole different ballgame. As MSCN Amer Awani notes from his direct experience managing a 60-megawatt PV plant, SCADA integration is an absolute game changer. By mapping the complete inputs and outputs of the switchgear directly to the SCADA system, a remote operator sitting miles and miles away can monitor breaker status, read electrical measurements, and clear protection trips. They get to do all of this safely without ever having to physically stand in front of a live, high-voltage panel.